Okay, in this video, we're going to look completely at the algebra of creating partial fractions, and we're not going to do any calculus in this video per se. So let us look at example one. This is a fairly easy one. We need to create partial fractions for this expression so that we could have two fractions where it'll be easy to get the take the integral. Right? But we want to factor the denominator. Right? So basically the one just stays put, and we're trying to figure out how to factor the denominator. And this is a very easy one. Both terms have a factor of x, and when we pull the factor of x out, we're left with an x minus 3. So how would we rewrite this then as partial fractions? We know that we must have a 1, or I'm sorry, we have two separate denominators we work with. We can look at both factors in the denominator here. We have a factor of x and we have a factor of x minus 3. Those will be the denominators for our partial fractions. So we're going to have a second fraction that has to have a denominator. We'll put a plus here with a denominator of x minus 3. Now we don't know, you might be tempted to just put a 1 here and a 1 here and think that you're done. We are not, we can't do that, all right? What we have to do is, instead of putting a 1 in those two places, my pen, we need to put unknowns in those two places. We don't know what goes there. So we will call those A and B. So we're going to use this relationship right here that we've boxed in to figure out what A and B should be, so that we will then be able to fully write the original expression in terms of these two partial fractions. So we're going backwards from what we usually do in algebra. Usually you're trying to take two fractions and make them into a single fraction with a common denominator. So this feels like backwards algebra. So, but the things that you're doing forward, you can run the other way, all right? So the easy way to solve this is simply multiply everything by the denominator that we have here. Multiply all terms in the entire equation by that denominator, all right? Now, when you do that to the left-hand side, so if you multiply the left-hand side by x times x minus 3, you simply get 1. Now, if you multiply the first term on the right-hand side by x times x minus 3, the x that's in the denominator will divide out the x in that product, and you're left with a times x minus 3. For the second term, when you do the multiplication, remember we're multiplying everything by x times x minus 3, we'll end up dividing out the x minus 3, so we'll have an x there. All right, so this will give us a little system of equations to work with. Let's distribute the a. 1 is equal to ax minus 3a plus bx. And then we're going to group. Notice we have two terms that have x. So we have an a plus b times x minus 3 times a. Now you'll notice that on the left-hand side, we don't have any x's. So what we can do is, on the left-hand side, we can add 0 times x plus 1. So what does that imply? If we need to have like terms equate. So on the left-hand side, you see that we have 0 x's, but on the right-hand side, we have a plus b of them. So what does that imply? That means that a plus b must be 0, so that the number of x's on the left will balance with the number of x's on the right. It also means, if we look at the left-hand side, we have a 1 here, and we have a negative 3a on the right. So this implies that 1 must be the same as negative 3a. Okay, so now we have a system of equations that we can solve for a and b. If we start with the second equation, it's quite easy. A ends up being negative 1/3. All right, and then we can substitute over. So negative 1/3 plus b must be 0. So the only possibility is that b is equal to positive 1/3. So we now know what a and b are. So we can rewrite the original expression, which was 1 over x squared minus 3x must equal, a was negative 1/3, so you could say negative 1 over 3x plus b was positive 1/3, so 1 over 3 times x minus 3. It's a nicer way of writing it than putting 1/3 in the numerator. Put that extra factor of 3 in the denominator. So this is the best way to write it. Now, we're not going to do the calculus right now, but you can imagine I could put integral signs with respect to x in front of everything. And as long as I do it for everything with respect to x, the two things would remain equal. And it's pretty easy to find the antiderivative of the terms on the right, where it was very difficult to figure out the antiderivative of the terms on the left. So that's example 1. Let's do a couple more examples here. Okay, so in example 2, I'm going to start with, we box this in, I'm going to start with 1 over x squared plus 2x minus 3. And I need to rewrite that. Well, if I want to rewrite that, I should factor the denominator, right? Sometimes factoring works out very, very nicely. In fact, all the problems that you're going to need to be able to do will have nice factoring. So we're simply going to do guess and check, all right? So we know that if we FOIL, the first two terms must both be x, so that when we multiply them together, we will get an x squared. Since it's a negative 3 at the end here, we must have a positive term and a negative term, and the only factors of 3 are 1 and 3. So we need a plus and a minus 3. So I'm sorry, plus or minus those two factors, and then we have to figure out the order. So 3 minus 1 is 2. 1 minus 3 would be negative 2. So we need to get a positive 2 out of this. So we must add the 3 and subtract the 1 in order to get a positive 2 as the middle term. And this will still be a 1 in the numerator for now. So the denominator factors nicely into x plus 3 times x minus 1. So notice these are nice examples. So I can write out, then I can write this out over the two different factors. So here are the partial fractions. One will have a denominator of x plus 3. The other will have a denominator of x minus 1. We don't know what goes in the numerators. Not a and a. We know that. Don't assume it's 1. Just write them as a plus b, or a and b, I should say, right there. And now we can use this boxed-in relationship to determine what a and b are. Okay, so like in the last example, we're going to multiply through by the total, the complete denominator, all of the factors of the denominator that I just circled. And so that will leave 1 on the left-hand side. When I multiply the first term times both of those factors, the x plus 3 will cancel. And so I'm left with a times x minus 1. And when I multiply the second term by both of those factors, the x minus 1 will cancel. So we have b times x plus 3. Like in the previous example, let's expand. We have ax minus a plus bx plus 3b. So let's group. So space, we have a plus b times x, and we have minus a plus 3b. That's what's left over. And remember the trick, you don't need to write it in, but we have 0 x's on the left-hand side, and we have a plus b x's on the right-hand side. So a plus b, that's how many x's we have, must be 0. And now we have to consider both terms at the end and equate those to the 1. So 1 must equal negative a plus 3b. All right, so the part underlined in green must add up to 0 x's, and the part in red is everything else. So that must add up to 1. So now I have a system of equations that I can solve. All right, now you could bring in matrices for this, but it's a 2 by 2. I think it's usually faster not to use matrices to solve systems of equations with 2 unknowns. So we're just going to do some substitution. Looking at the right-hand equation, I could bring a to the left-hand side and say that a is the same as 3b. I can substitute over, so I have 3b plus b must be 0. That's 4b is equal to, whoops, we have a mistake here. Let me pause and find the mistake because we can't have everything equal to 0. Let me quickly find my error. Error found. It was in the previous step. So let's get rid of this. This would be a bad thing to do because I forgot about the 1. Given that the 1 is over here on this, in this equation, we should start with the left-hand equation. It's the simpler of the two, and say that a is negative of b. And therefore, if we sub that over, 1 is equal to negative a minus 3b. This will work. 1 is negative 4. I'm sorry. This should be, we can put negative b in for a. So we have negative 4b. So the substitution was that negative b went in for a. So now we have negative 4b must be 1. So b must be negative 1/4. Sub that back. And a is negative of b. So a is positive 1/4. Now that I have that, I can rewrite the original problem. So I can say, remember the original was up there, a few lines up, I can say that 1 over, do that better, 1 over x squared plus 2x minus 3 can be rewritten as 1. We'll bring the 4 of the quarter down to the denominator, and we have an x plus 3. And then we have minus, because b was negative, 1 over 4 times x minus 1. And these partial fractions then would allow me to integrate that complicated denominator. So that's example 2. Let's move up and do example 3. It'll be of the same sort. So notice everything that we've had so far is quadratic, and the quadratics break into 2 linear factors. So we're going to continue that pattern. So example 3, we're going to write 1 over 2x squared plus 5x minus 3. Right. That will factor, or so we hope. We're going to see if this can factor. It does, because I've rigged the problem. They don't always factor, but the ones in this section will, because the problems are rigged to do so. So the denominator can factor. To make it work, I must have a 2x and an x in the lead terms. We know for factoring, this must be a 1 and a 3 as factors. We just need to figure out the right way to put them in so that we can get a positive 5. And I think that the best way to do that is, remember, 2 times 3 is 6. So let me put a positive 3 there and subtract a 1 there. So there are just a couple of options you could guess and check. Since I've done a number of these, I guessed that very quickly as the 2 options for this, right? So that's what actually went right to the partial fractions. The denominator must be a combination of those 2 things. Let me actually rewrite that not as partial fractions yet. Let me write it over a single denominator. Whoops. So we had determined that's an x plus 3. That's a 1. And so this has partial fractions of a over 2x minus 1 plus b over x plus 3. This equation will allow us to figure out what a and b are. Okay, so we do the same thing that we did before. We multiply by the entire, both factors of the denominator here, and we end up with 1 is equal to a times x plus 3, because the 2x minus 1 will cancel, plus b times 2x minus 1, because the x plus 3 will cancel. Right, so let me just work through this a little bit faster now. All right, and then we can group. So we have 1 is equal to a plus 2b times the x's, and then we have 3a minus b left over. So like before, we have a 0x out here, which you don't have to write, but that tells us that a plus 2b must equal 0, and 3a minus b must be equal to the 1. Okay, so once again, notice the left-hand equation has fewer non-zero terms, so we're going to want to work with that. And we can say that a is the negative of 2b. Substitute that over. And I'll say 3 times the negative of 2b minus b is 1. So if you total that up, that's negative 6b minus b. So negative 7b is 1. B is negative 1/7. Sub that back. And a must be positive 2/7. So we can rewrite the original expression. 1 over 2x squared plus 5x minus 3 must equal, a was 2/7, so put the 2 in the numerator, 7 in the denominator. We have a factor of 2x minus 1. And then b is negative, so minus 1 over 7 for the 1/7 times x plus 3. Those two terms will be things that aren't hard to integrate. Okay. We'll do one more example where we have a quadratic expression in the denominator. And quadratic expressions factor nicely, or can factor nicely. So this will be one more that factors nicely. In fact, I'm going to have you do some of the steps with some pauses here. So we can write the original problem, which you wouldn't know, so I better write it down. Oh, actually, this is a unique example, so we'll do this together. See if you can figure out the factors. So go ahead and pause the video and see if you can figure out what to put in the parentheses there. Hopefully you realize this is a perfect square, so x plus 1 and x plus 1. Now this leads to a problem, because if we simply put x plus 1 plus x plus 1 with an a and a b, this just does not work. It will not work. So there's a trick to this. Notice we have a repeated factor. In all of the examples so far, there were no repeated factors. So if I look up at the examples that we've had before, 2x minus 1 and x plus 3 are different. The example before that, x plus 3 and x minus 1 are different. There are no repeated factors. But here, x plus 1 is a factor twice. We could have written that as x plus 1 squared. So the way we handle this is the new thing, is we have to consider a denominator of x plus 1, and we have to consider that x plus 1 squared could be the factor, right? So let's go ahead and look at this. Okay, so doing the same thing that we did before, it's going to turn out this will be an easy problem. We multiply everything through by x plus 1 twice. So the left-hand side becomes 1. On the right-hand side, one factor of x plus 1 cancels when you multiply the first term by x plus 1 squared. For the second factor, both of the x plus 1's cancel. So we're left with this. All right, so let's distribute. All right, and then we can simplify. We can see that we have 1 in both on both sides. So let's say 0 must equal ax plus b. Now in green, I'll write that's really 0x plus 0. So what does that mean? We can write two equations. Whoops, I think I have an error in here. So let me find my error real quickly. Okay, I found my error. Let me get on my red pen to fix it. Right? When I distributed the a, I shouldn't have had ax plus 1. I should have ax plus a. And then that means I can't subtract 1 from both sides. So this 0 is really a 1. So then if I keep on going, this is a plus b. All right, so back to where we were. Okay, so ax must equal 0x, so a must be 0. And likewise, a plus b must match up with the 1, so 1 is equal to a plus b. Now, if a equals 0, then 1 is equal to 0 plus b, and b is equal to 1. So what we have here is we could have written the original expression 1 over x squared plus 2x plus 1 could be rewritten as no a's, so just 1 over x plus 1 squared. All right, and that should be fairly obvious why that works. So the a value must be 0. Let's do one more of these where all I'm going to do is change that to an x in the numerator from example 4. So for example 5, I'm going to change the problem to x over x squared plus 2x plus 1. So we know from example 4, that must be x over x plus 1 times x plus 1. We still have the repeated factor. So we can, just like in example 4, say this is a over x plus 1 plus b over x plus 1 quantity squared. So notice everything matches up with example 1 except the 1 in example 4, the 1 is being replaced by the x, right? Now let's see what the consequences of that are. If we multiplied through by the denominator, we end up with the expression that x, when we're working with this part of it, is equal to a times 1 factor of x plus 1 plus b. So x is equal to ax plus a, distributed correctly this time, plus b. So now remember, we have 1x this time, all right? You could write a plus 0 though, okay? So the constant term is 0 this time, not the x term. So if I work through that, ax must equal x, therefore a must be 1. And a plus b must equal 0. So if a is equal to 1, we can sub that in. 1 plus b is 0. B must be negative 1. So I can rewrite what we started with, x over x squared plus 2x plus 1. I can rewrite that as a, which is 1 over x plus 1, plus b, which is negative 1. Oh, so let me subtract instead of adding. I can say That's minus 1 over x plus 1 squared. So there we have it. Let me stop with that, and I'll do a couple more more complicated examples in the next video.